today we're going to graph tangent and cotangent with the same idea of just pulling values from the unit circle and plotting them, connecting them with the smooth curve to see what those graphs do in fact look like. That's a technique we can take with any graph when we're not sure what it looks like. They do come from the unit circle, and it does generate those values, which is what we're seeing in this GIF. Okay, so at 0, we know that our tangent value is our y value over our x value. So at 0, my y value is 0 and my x value is 1, and so 0 over 1 is 0. So the tangent is at the origin. When it's at 0, it's at 0. At pi over 4, both coordinates are root 2 over 2 and root 2 over 2, and they're both positive. Anything over itself simplifies to 1. So at pi over 4, our tangent value is 1. So I'm going to go ahead and mark 1 on my y-axis. At pi over 2, my y value is 1, but my x value is 0. We know division by 0 is undefined in our number system, and graphically, when we have division by 0, that generates a vertical asymptote. So tangent has a vertical asymptote. Okay, so just right here, moving left to right, connecting with a smooth curve, we can see that our tangent graph is increasing, and it's going to be approaching that asymptote. Okay, at 3 pi over 4, both coordinates are root 2 over 2 and root 2 over 2, but we're in quadrant 2, which means my x value is negative, so that's going to simplify to -1. So at 3 pi over 4, put a -1 on your y value, and we're at -1. At pi, my y value is 0 and my x value is -1. 0 over anything is 0. So we're back to 0. And so from the vertical asymptote, if we connect those with a smooth curve, we're coming from the vertical asymptote, increasing through that key value on the way back to the midline. And it turns out, as we'll see just in a second when we try to go further, this is one full cycle of tangent. That's all tangent's got to show us. From here on out, it's just a repeat. So if we go to 5 pi over 4, both coordinates are root 2 over 2 and root 2 over 2. But now we're in quadrant 3 where they're both negative. So the negatives cancel, and that generates a +1. So again, we're at +1 again. And if we kept going, it would just repeat. So what we see is that one full cycle of tangent starts and ends at the midline. And so 1 and -1 are no longer the maximum and minimum, but they are still key values that we pass through as we're either approaching the asymptote or coming from the asymptote back to that midline. So let's practice a few more cycles of those because we're going to use transformation rules to graph, so we want to be really good at graphing a parent function. So every pi units, and that's important. How long did it take us to see everything tangent had to show us only pi units? Tangent and cotangent are the only two trig functions that don't have a parent function with a period of 2 pi. So every pi units, we have a full tangent cycle. I like to say this, tan assy in the middle. It helps me remember that on tangent, there's an asymptote in the middle. So at the half pi's, I'll have an asymptote. And then tangent is an increasing function. And so that's good to remember. Tangent is an increasing function. It's increasing. So as we move to left to right, it's increasing. So coming from that midline, we're going to be increasing through that key value on the way to the asymptote. And then from the asymptote, we'll be increasing through that next key value on the way back to the midline. Okay, so that's one full cycle. So let's try that again. So we're going to go midline to midline, tan assy in the middle, increasing through the key point, increasing from the asymptote through the key point back to the midline. So that's one cycle of tangent. Okay, what is our domain? Well, it goes forever and ever in both directions, but it's not all real numbers. It's all real numbers such that x does not equal. Where are those asymptotes happening? They're happening at the half pi's, so we're going to call that pi over 2 plus k pi, where k is an element of the integers. Why is it plus k pi? Remember, we have to start on the half pi's, but we don't want every half pi, or that would also include the whole pi's. So it's pi units from asymptote to asymptote. So we're going to start at a half pi and go forward an integer multiple of pi, so that makes it forward or backwards pi units, and we'll hit another asymptote. Our range is all real numbers. Our asymptotes happen everywhere where our domain was restricted, so that x does not equal pi over 2 plus k pi. That's why those were domain restrictions, because that's where our vertical asymptotes are at. So we already know how to describe them. Oh, and I said k is an element of the integers. I was copying it there and see that I wrote pi, where k is an element of the integers, capital Z for our integer function. Again, you can put a double bar on it like the all real numbers if you want. Okay, x-intercepts, we've got an infinite set of them, and it looks like they're happening at the whole pi's. So we'll say the set of all k pi, where k is an element of the integers. And those are my x values, so I'll go ahead and put x equals. Whether or not you use the set notation, I'm not really particular about on this, but you are describing it with set notation. So whether or not you have the curvy set brackets, not as important, but you do want to describe it with set notation. All right, so is it an even or an odd function? It's an odd function. If you take a look at it, that's a 180-degree rotation about that origin. So that first half of the tangent cycle that's in blue to the right of the y-axis, if you rotate that 180 degrees, it should rotate and lie exactly on top of that orange part of the tangent cycle, also closest to the y-axis. So that's a 180-degree rotation, which makes it odd, which means if we have a negative b value, we're going to do something odd with that negative. F of negative x, we know equals negative f of x. For odd functions. So for odd functions, we can do something odd with that negative. We can bring it out front. So it ends up out front there. Okay, f of negative x equals negative f of x if it's an odd function. It's an increasing function, so there are no intervals of decrease. There are no intervals of decrease. Okay, you can put none or empty set. But intervals of increase, you've got a lot of them. So let's just describe them from negative pi over 2 to 3 pi over 2. So they're going to be non-inclusive because they're coming from asymptotes. So negative pi over 2 to pi over 2, non-inclusive, union with pi over 2, non-inclusive from the other side of that asymptote to 3 pi over 2, the next asymptote. And then we can just do the ellipses to show that that pattern continues. Y-intercepts, there's only one. It's at the origin, and that's a coordinate point, not an interval. All right, so that's our tangent cycle. Once we're really comfortable with tangent cycle, we'll use it to graph our cotangent cycle. So let's take a look at that. So I copied our tangent values and our tangent graph. Cotangent is the reciprocal, so it's going to be the flip of that. So let's see how that works out. So when 0 came from 0 over 1, so when we flip that, that's going to give us 1 over 0. Again, division by 0 is undefined in our number system, and graphically, that's going to look like a vertical asymptote. So when tangent was at its midline, cotangent is at a vertical asymptote. 1 over 1, when you flip it, it's still 1. So both tangent and cotangent are at 1 at pi over 4. The undefined came from division by 0. So when we flip that, that's 0 over 1. 0 over anything is just 0. So where tangent had a vertical asymptote, cotangent actually is at the midline. Negative 1 flipped is still negative 1. So at 3 pi over 4, both tangent and cotangent are at negative 1. That 0 is 0 over 1. When we flip it, it's undefined, which generates a vertical asymptote. And so that, if we connect that with a smooth curve, moving from left to right, we're coming from the asymptote through those key values on the way down to the other asymptote. And there in purple is one full cycle of the cotangent function. Those are our 5 key points. 2 are the asymptotes on the outside. So I remember cotangent, the OT in cotangent makes me think of outside. The asymptotes are on the outside. So the cycle starts and ends with the asymptotes on the outside. It's at the midline in the middle, and then it's a decreasing function. So cotangent is decreasing. Cotangent is decreasing. Okay, and so that's how you can tell tangent and cotangent apart. Of course, with reflections across the x-axis, we could make either of them look like each other if we did reflections and shifts, which is possible with transformations. So just like sine and cosine, secant and cosecant, they can be written as transformations of each other. But as far as the parent functions, tangent's increasing and cotangent is decreasing. Again, if we want to see what happens if we continue forward at 5 pi over 4, we said that that's 1 over 1, which when we flip it is still 1. So at 5 pi over 4, they're both at positive 1. And of course, that pattern is just going to repeat. So we said asymptotes on the outside every pi units. The period for cotangent is also pi units, and it's a decreasing function. It's at the midline in the middle. So we're going to come from the asymptote through those key points on the way down to the asymptote. Very quick to graph. Let's try another one. So we said asymptotes on the outside. So every pi units will have an asymptote, midline in the middle, decreasing. So it's coming through those key values from the asymptote through those key values on down to the next asymptote. Last one, every pi units, we get an asymptote, midline in the middle, decreasing from the asymptote through those key points down to the next asymptote. Okay, so there's 4 cycles of our cotangent function. Now, again, for me, the way that I remember to keep these apart, a teacher recommended this one time, and I was like, not really, but then I actually remember it, so it's kind of funny. She said cotangent kind of looks like a C, which I'm like, not really, it doesn't look like a C, but it looks way more like a C than tangent does. So if you think about that, tangent definitely doesn't look like a C. Cotangent, maybe kind of, more than tangent. So it helps me remember, oh yeah, that's the cotangent graph when I'm trying to tell them apart. You do what works for you, I'm just sharing memory tricks. Domain of cotangent is all real numbers such that x does not equal, where are those asymptotes at? They're happening on the whole pi, so that's just the set of all k pi, where k is an element of the integers. The range is all real numbers. Asymptotes happen where the domain is restricted, so that's x equals k pi, where k is an element of the integers. X-intercepts, there's an infinite set of them happening at the half pi's. So how do we describe the half pi's? X equals the set of all pi over 2 to get us on the half pi's. And then remember that they are pi units apart. So that'd be plus k pi, where k is an element of the integers. Okay, so that's where our x-intercepts are happening on the half pi's. This is an odd function. Again, you can check for origin symmetry by drawing a line from any point to the origin, same distance on that same line, you should hit a point. Any point to the origin, same distance on that same line, you should hit a point. Any point to the origin, same distance on that same line, you hit a point. I think that's a great way to check for origin symmetry. It does in fact have origin symmetry. So it is an odd function, which means what are we going to do when we have f of negative x? A negative b value, we're going to do something odd with it. We're going to bring it out front. F of negative x equals negative f of x for odd functions. Intervals of increase and decrease, well, because this is a decreasing function, there are no intervals of increase. It's intervals of decrease. Let's just list them between negative pi and pi. So the pattern will continue. Again, we're coming from asymptote, so that'll be negative pi to 0 non-inclusive union with 0 non-inclusive to pi non-inclusive, and then a dot, dot, dot to show it continues. Y-intercepts, this time there are also none of those. I'm just going to put the empty set because we have a vertical asymptote at the y-axis. Take a look at the next video to see examples of graphing with transformations on a few of those parent functions.